So we are very pleased to have Professor Catherine Mondloch with us today in our Bar-Ilan University Vision Science Seminar. Professor Mondloch did a BA in psychology at the University of Western Ontario and graduated with honors. She then did a PhD in psychology and biology at Indiana University, and then became an assistant professor at King's College. After moving to McMaster University, she joined Brock University, where she is now a professor in the Department of Psychology and heads the Face Perception Lab. During that time, she was also an associate investigator at the Australian Research Council Centre of Excellence in Cognition and its Disorders and an adjunct faculty at the University of Toronto. She has recently published books about essentials of lifespan development. She authored 9 book chapters, and she published almost 100 refereed scientific articles, including in Nature, in Trends in Cognitive Science and Developmental Science, and in many more distinguished journals. She has an H index of 46, according to Google Scholar, where her publications have hundreds and even thousands of citations. She was an associate editor of the Journals of Experimental Child Psychology and is currently on the editorial board of the Journal of Experimental Child Psychology. Sorry, I got this wrong. She has given many invited talks across the globe and has received many academic distinctions and awards for her research excellence and creativity for her mentorship. She heads the Face Perception Lab, where her research focuses on investigating the developmental, perceptual, cognitive, and social psychological aspects related to face processing, where she combines cutting-edge technology as eye trackers, 3D cameras, and electrophysiological signals. So we're very pleased to have you today with us in our seminar and are looking forward to hearing about your exciting research. And thank you so much for joining us. And I'm sorry about the mistake I made about the editorial board, but I hope this can be corrected.
No, that's fine. No, so thank you for having me. I'm just going to warn you that it's telling me my internet's a little unstable, and I think that's because we're in the middle of a storm. So hopefully this goes fine. So I'm going to share my screen, and I think once I do, I won't be able to see anybody. So just let me know if there's a technical problem.
Sure.
So let me just go here and there. Okay, everybody can see the screen now?
Yeah.
Okay, great. Okay, and I can see some people. Okay. All right. So thank you for having me. And I was saying to Sharon, what I'm going to do today is try to tie together 2 different lines of research for you. So all of the data I'm going to show you today has been published, but it's all over the place and some of it's quite recent. And so I thought what I'd do is integrate our work on group differences and individual differences in face recognition. So before I start, I just wanted to acknowledge that the work is funded by NSERC, which is the Natural Sciences and Engineering Research Council, as well as the Canada Foundation for Innovation. And I want to acknowledge these 5 people who really drove this research program. You might know some of them. Sarah Lawrence was a postdoc, and she's now on faculty in the UK. Claire and Xiaomei and Kristen were all PhD students and are now all over the place. And Vince, you'll just meet a little bit at the end. He was absolutely brilliant undergrad. He came to me with ideas and would correct my writing. He's great, and he's now a PhD student in the States. So this is really their work that I'm going to tell you about today. So let's start with why I study face recognition. It's something that we rely on every day. So from an applied perspective, it's really important. So we need to recognize our colleagues. Children and teachers need to be able to recognize each other. Kids need to recognize each other on the playground. Older adults need to recognize friends at a community center or their neighbors. And I'll just back up. We're really good at this. So most of us make no errors when it comes to recognizing familiar faces. And for this reason, we're pretty comfortable with relying on photographic ID in lots of settings. So We'll present our ID to buy age-restricted goods. We present ID to cross borders, access healthcare, etc. And the assumption here is that we're also good at deciding whether the person standing in front of us is the person depicted in their ID. But it turns out that we're actually quite error prone when it comes to matching identity in images of unfamiliar faces. And so what I'm interested in is how experience shapes all of these skills. Now, you probably, if you think back to your research career, can imagine one paper that really shaped your whole research program. And for me, it's this paper here. It's a beautiful paper by Rob Jenkins and colleagues at the University of York. And what they did was very simple, but it drove home the point that familiarity with a face really matters. So some of you might know this, but I've got to talk about it because it basically this is what we're doing. So what they did was they gave participants a stack of 40 photographs. You can see that unlike traditional images in face perception research, where everybody's got a neutral face looking at the camera, wearing cloth over their clothing, hair mask, these are what we call ambient images. So they're naturalistic images where viewpoint varies, expression, camera, lighting, people might age. In the case of women, you'd see changes in makeup. So there's lots of within-person variability as well as differences between people. And what Jenkins did was just ask people to sort these 40 pictures into piles so that each pile included all of the images of exactly one person. So the number of piles you make is a measure then of how many different identities you perceive. And what they didn't tell people was that in this stack of 40 pictures, there were only 2 identities present. So there's really 20 pictures of 2 different people. Now, some people were very familiar with these faces, and they performed perfectly. They made exactly 2 piles. It's trivial to do this task if you're familiar with the identities. But when people were not familiar with the identities, they made an average of 7.5 piles. So they thought there were 5, 6, 7, 8, or 9 different people there, when in fact there were only 2. And I just did this demonstration with my class. I teach on Monday nights, and they performed exactly like this. You get it every time. So what this told us was that it's hard when we have these ambient images to tell faces together or to recognize somebody across different images when their appearance is allowed to vary. And this better captures the kind of thing that we have to do every day. So this has really shaped our work over the last 8 years. Now, I'm a developmental psychologist, and so I'm really interested in experience. And so as soon as I came across this paper, which was a couple of years after it came out, it struck me that we could use this to look at whether lifelong experience impacts identity matching of unfamiliar faces, as well as the ability to recognize highly familiar faces, so people that you know. And then we could also look at how lifelong experience impacts face learning, or the process by which a new face becomes familiar. So I'm going to tell you this story, and then I'll move over to individual differences and try to tie them together. So how do we look at the role of experience? Well, the main way that we've done that in the lab, or our starting point at least, was to look at age-related change during childhood. And the logic here is that as children grow from, say, 4 to 12 years of age, they're gaining more and more experience with faces. They see more different unfamiliar faces, but we think more importantly, they come to know more people. So they have more familiar faces represented in their face space, we call it, this mental representation. And so it could be then that as they gain experience, they become better at face matching, face learning, and then familiar face recognition. Oh, sorry, yes, I see a hand. No, okay. Okay, and so the problem though, whenever you study age-related change during childhood, is that those changes might be due to experience, but they could also be due to general cognitive development, things like memory and attention. So we need to look at other group comparisons as well. And so one comparison that we've made is between young adults being tested with own as compared to other race faces or other ancestry faces. So the logic here is that most adults and all of the adults that we test have much more experience with own race faces than other race faces. But it's the same brain who's doing both tasks. And so if we get the same pattern of results when making this comparison that we get when examining children, then we have a hint that experience really does matter. But even if we see the same pattern of results for these two group comparisons, it wouldn't eliminate a role for general cognitive development. And so in all of this work, we've also compared young and older adults. And the logic here is that older adults have, if anything, more experience with faces than young adults. So if experience matters, they should be the best at this task. But the older adults show declines in the same cognitive skills that have prolonged development during childhood. So if they show the same pattern of results, that would tell us that general cognitive skills also play a role. So we've done all three lines of research for all of our tasks. I'm not going to tell you about all of the tasks today, but over the years, we've had a big sort of spreadsheet on the lab wall, and we were clicking off boxes as different students filled in the pieces. So I'm going to tell you the story about this today. And we'll start with identity matching of unfamiliar faces. So in order to look at this, we decided to adapt the Jenkins sorting task to make it child-friendly. And so we took this shoebox and just decorated it to look like Buzz Lightyear's spaceship. At the time, Buzz Lightyear was a very, very popular movie. And we gave the children a stack of photos that included different pictures of Buzz, so it's within Buzz variability, intermixed with pictures of another character, and they were asked to put all of the pictures of Buzz into the spaceship while keeping other characters out. And I'll just tell you that all the children did perfectly on this task, so we know that they understand the task itself. Then we gave them another shoebox, and on this shoebox, which was decorated like a toy house, we put a picture of a woman with whom the child was unfamiliar. And you'll see why later, but this is a teacher from a school other than the school that the child attended. So she was completely unfamiliar. We'll call her Alice. And so again, we gave children a stack of photographs, and they were asked to put all of the pictures of Alice into the house while keeping out everybody else. Now you have to make sure that children understand the task and stay attentive. So we had some attention checks. So we included 4 images that were exactly the same as the face on the front of the house. And we included 4 images of a woman who looked completely different. And again, the children did very well on these, so I won't speak of them anymore. The key stimuli are these. So we had 9 new images of Alice, and they were intermixed with our attention checks and with 9 images of a similar distractor. And there were many different pairs of these images. So what we're going to measure here is D prime, and I'm just going to define that in case there are students listening that aren't familiar. So we defined a hit here as putting a picture of Alice into the house, and a false alarm as putting in a picture of the other woman. And what this does then is allows us to calculate D prime, which is a measure of sensitivity. It's your ability to tell apart the target from non-targets. So high D prime scores are better. Okay, so here's the data then from our child participants. And what you can see on the y-axis is D prime. So again, higher scores are better. Age on the x-axis. And you can see that we have a correlation here between age and D prime, such that children are getting better with age. There's lots of spread in the data. Rob Jenkins got exactly the same thing. As we'll see later, some people are just better at this than others. But we seem to see age-related improvement. And of course, what we don't know is the extent to which this is about experience versus general cognitive development. So now we can go to our other 2 comparisons. So what we then did was we tested people with own and other race faces. This was done with Sarah and Xiaomei, and you can see multiple images of each of them here. And in this study, what we did was we tested both white and East Asian participants. The White participants were tested here in St. Catharines, which is quite a homogeneous area. And the East Asian participants were tested in China, in Jinhua, which is also very homogeneous. So Xiaomei got a trip home to collect this data. And what I'm going to show you on the next figure is the number of piles made by each participant. So I'm going to show you individual data, remembering that the correct answer is 2. So here you can see number of piles on the y-axis and participant rates on the x-axis. So the 2 left columns show you our participants here in Canada, and the 2 right columns show you East Asians. So the first thing you'll notice is that there's lots of spread, just like we saw with children. But sorting of own race spaces is shown in blue, and other race spaces shown in white. And those red lines show you the median. And so what this tells us is that people made twice as many piles. They thought there were twice as many people when sorting other as compared to own race spaces. And this was really interesting because up until now, the other race effect had always been characterized as a problem of discrimination. So if you go into the literature, you'll see titles like "They All Look the Same to Me." And what this showed is that when you have ambient images and when you don't constrain the options, the problem actually is one of telling together. So this suggests then that our findings with children are at least partially attributable to experience. But what about older adults? So for older adults, we had to adapt the task again. And so what we did was turn it into a matching task. So they saw pairs of faces and they were asked, is this the same person or 2 different people? So here's some examples there. And again, we can calculate D prime, and you can see that young adults in blue are outperforming the older adults in red. So this would suggest that general cognitive skills also influence our ability to decide whether different images belong to the same person or different people when we are unfamiliar with the faces. Okay, so we know then that there are group differences in identity matching of unfamiliar faces. So now what we can do is go and look at recognition of highly familiar faces. So let's just think for a minute about what this is, just so we have a conceptualization. So I've just made this up, but this might be my mental representation of this unfamiliar person and their distractor if the faces are unfamiliar. So I can't tell different images together, and I've got pictures of the distractor intermixed with Alice. But as Alice becomes familiar, what's going to happen is I become very familiar with her face, and it's easy for me to group images, easy for me to tell faces apart. So what we want to know now is, do young children, for example, get to this point? So we use pretty well the same tasks, but now on the front of this shoebox, it's a picture of the child's own teacher. So this took us more than a year to do because we needed teachers who were willing to give us pictures, and then children in this classroom whose parents provided consent. So you can imagine that took some time. But the task is identical, and here's the data. So at first I blocked out the younger children, but what you can see is that by the time children are 6, they're performing really well. The odd mistake here and there, but essentially these children are adult-like. So that tells us that even though they struggle more than young adults with identity matching of unfamiliar faces, they can build a representation of a face. But look at the data from younger children, our 4- and 5-year-olds. Some of them are doing really well, but many of them are making a lot of errors. And when we look at the errors, it's not a problem of discrimination. They almost never put the stranger into the house. It's that they're too conservative. They're not recognizing all of the different images of their teacher. They're setting them outside of the house. So this suggests then that by 6, we can build a good representation of a familiar face, but younger children seem to struggle in doing that. And I should say that these children had been in the classroom for at least 3 months and as many as 9 months. And there was no effect of that at all. So something different's going on here. So we published this paper a while ago now. And at the time we said, well, maybe the problem is that teachers don't provide enough variability in appearance because they come to school looking professional each day. They're under those fluorescent lights. The 4 and 5-year-olds haven't seen the teacher coming home from the gym or dressed up for a wedding. And so maybe they just did not provide the training that young kids need. So subsequent to this, we decided to test this young group again with the face that they should know best of all, and that's the face of their parent. So we got parents to give us pictures and tested children with their parents' face. But what we did was we collected 2 sets of images from each parent. One that was taken after the child was born, and one that was set from before the child was born. So the logic here is if what these children are missing is exposure to lots and lots and lots of variability, they should get that from their parent. But it's this problem for these young children is that they just, regardless of variability, can't go beyond their own direct experience. They can't extrapolate to new variability. Then they should have a problem with these pictures taken from before they were born. So here's the data from that. So I'm showing you now the data from pictures taken after the child's birth. And that red box just shows you children that are 4 and 5-year-olds that struggled with their teacher. You can see there are some errors here, but there's no affected age. So the children that were 4 and 5 did not perform differently than our 6 and 7-year-olds on these images that fall within their range of experience. But when we test them with images taken before they were born, so images that require them to recognize their parent looking differently than they had before, now we get an effective age. These younger children are struggling. So this suggests that the problem for them is that they can't extend beyond their own direct experience, or at least some of them. So this is something that we want to follow up on, but haven't been able to yet. Okay, so what about own versus other race-based? We went back to China for this study, so all of these participants were tested there. You can see on the right here, we replicated our earlier findings, so twice as many piles for unfamiliar other race as compared to own race. This was a new set of images, so we just wanted to check. But look on the left, these are familiar faces. So these were images of Kristen Stewart and Emma Watson, who are actors in the Harry Potter and vampire movies. These were very popular at the time. And you can see that people basically performed without error. They made 2 piles, which means, again, even though they struggle at identity matching of unfamiliar faces, they can build a good representation of a familiar face over time. What about older adults? So here the task was, is this an image of Justin Trudeau, the Canadian Prime Minister? And so this would be, and this would be, and this would not be. And what we found here was that older adults, like young adults, are at feeling 97, 96%. So what this tells us then is that although we have group differences in identity matching of unfamiliar faces, we're not seeing that. That red X is translucent because I'm hedging a little here, but we're not seeing that for familiar faces with the single exception of 4 and 5-year-old children. There seems to be something different there. So now we can go and look at the process of face learning. And we've looked at face learning in many different ways. I decided to just pick one for today, because otherwise we'd be here for a very long time. And so here what we're looking at is the ability to recognize new images of a newly learned face in a memory task. So how do we do this? Well, we started this work with children, and so we had to get creative on how to get children to learn a new face, because they don't feel obliged to complete an experiment if they don't find it interesting. So what we did was we filmed different models who read a chapter from Teddy Bear Robinson's Day Out. So it's a great children's book, and it takes about 10 minutes to read that chapter. So this is one of our models. And what you can see here is that we filmed each model 3 times. So on 3 different days. And across those 3 days, we asked the models to vary their appearance. So they changed their hairstyle, their makeup. They're closed, not in any extreme ways, but as they would normally do on day-to-day basis. We use different cameras. We filmed in different settings. So we had natural lighting, fluorescent lighting, and we were outdoors. We changed distance. So we created lots of variability in appearance. And then in these studies, we had 3 conditions, but I'm only going to talk about 2 today for reasons we can discuss later if you're interested. But one was a low variability condition where they just watched a video as it had been filmed. That's what I'm not going to talk about. But the other condition was a high variability condition where we spliced the video so they got a third of the video from each of 3 days. So the idea here is that we're trying to create something akin to encountering somebody a few times, experiencing variability, and then can we recognize them later? And we compare that to a control group that only gets to see a single image of the person. Okay, so that's out. All right, so here's the recognition task. It's just like what we did before. So we have 9 new images of the model, intermixed with 9 images of a similar distractor. And then we also have control images or attention checks where we've just extracted images from the video because we want to make sure that our children recognize the model as they saw her. Otherwise, it'd be hard to interpret our data. And they all do just fine. They love this task. Okay, so how did they do? Well, what you can see here is mean D prime on the y-axis again. We have the 1 image condition, so they just get to look at an image of her. And then on the left, and then the high variability condition on the right. Children are in blue, adults in green. And what you can see here is that we get 2 main effects, but not an interaction. So in both groups improve from 1 image to high variability, and adults outperform children in both conditions. But interestingly, both groups show the same amount of gain from watching this 10-minute video, which means that children are learning, but after 10 minutes of experience, they're still being outperformed by adults. It's going to take a lot more experience for these children who were 6 to 12 to catch up to adults and perform as well. So presumably they're building a face representation more slowly at the same pace, but it's going to take them longer to get to that outcome. All right, so what about our other 2 comparisons? And unfortunately, all of these figures are arranged a bit differently because they're from different publications, but essentially we're getting the same thing. So here we have participants learning own and other race faces. And what you can see is that in both conditions, they're getting better from the high variability video as compared to 1 image, better for own and other race faces, but no interaction here. And we see something very similar for older adults, where like young adults, they improve in this high variability condition, but they're being outperformed by young adults in both cases. So what does this mean? It means that we have group differences in identity matching of unfamiliar faces. We have group differences in performance on learning tasks, so D prime being better in some groups than others, but not very much in the way of differences in the amount of improvement during learning or in familiar face recognition. So before we look at individual differences within young adults, I want to just try to link this to a model, which is the deep convolutional neural network models of face recognition. So these models, and I don't know how to run these models, but I find them interesting. But these models, they're modeled on the human visual system, and they're becoming very good at recognizing familiar faces. And so it struck me that we can look at how these models become very good and ask whether that might help us understand our group differences. And my reasoning here is that if we see similar group differences, it doesn't necessarily mean they're being driven by exactly the same thing. So how do you train a DCNN? Well, there's 3 stages of training. I'm only putting the first 2 here because they're what matter for today. The first stage is what we call face knowledge history. And what's happening here is the DCNN is being trained with a massive face set, millions of images, thousands of people. And this is to build a generic face space. And critically, each image that it's fed is labeled. So you're telling the model, these images belong to the same person, and these images belong to different people. After that stage is the face learning history. And this is where you train the model on stimuli that are similar to the test stimuli, similar to the kinds of faces that you want the model to recognize. So if I wanted the model to be very good with East Asian faces, at this point, I would train the model on that. If I wanted it to be very good with older adult faces, I would train the model on those faces. And again, each image is labeled. And the idea here is that you're building an expert face space. So I suspect what's going on here is that for young adults being tested on other race faces, the problem is a lack of face learning history, that they have this expert face space, but it's not for other race faces, it's for own race faces. So that would explain our other race effect. But in thinking about the younger children, what seems to be lacking, what I think is lacking here, is the face knowledge history. And my reasoning here is that young children see lots of faces. They see them in the park and at the grocery store. They haven't seen as many faces as an adult, but they've seen a lot. But most of those faces aren't labeled, right? You don't have parents saying, oh, that person over here by the carrots, we saw them earlier in the meat section. We're not training the child how to recognize the cross variability. They only do that for very, very few faces. And we suspect what's going on, why we see a big shift at age 6, is it's when children go to school that suddenly they're getting this training where they have to know lots of different faces, and they start to label them and learn about within and between person variability. So Sarah Lawrence and I have a plan to test this by comparing children in the UK versus Canada, where they start school at different ages. But this gets us thinking about young adults, because I showed you that there's lots of individual differences. Some are doing much better on unfamiliar face matching tasks than others. And so could it be that individual differences in face matching in young adults predict individual differences in learning? Now, Rob Jenkins published a paper showing that on average, adults know about 5,000 faces, which is a tremendous number, but that there's big variability here, ranging from, if my memory serves me, from about 1,000 to 8,000. So individual differences then are something that we can look at. Now, we haven't looked at that correlation, but we've started looking at individual differences. And this work was really driven by Kristen Baker. This was part of her PhD. So what Kristen wanted to do, first of all, was ask whether there are stable individual differences in unfamiliar face identification. There are a few studies out there on individual differences, not many. There's a call for more of these, but nobody had looked to see whether these differences were stable over time. And the focus had always been on D prime, and as you'll see, we wanted to look not only at D prime, but also now criterion. And this is because sometimes we see group differences in how liberal or conservative people are. And so this becomes interesting. So what Kristen did, and this was during the beginning of the pandemic, she was right in the middle of an EEG study and had to pivot on her PhD quite quickly and did a remarkable job of that. So what she did was she administered online 4 different tasks, all of which test people's ability to match identity of unfamiliar faces. First of all, in the upper left there, you can see that she figured out how to do the sorting task online. So she programmed this. People don't always cooperate by keeping the images such that you can see them all. So she had to figure out how to replay overlapping images, but she did that. And so what we can measure here, just like Rob Jenkins, is the number of piles that people make, but also we can measure confusion errors. So the number of times that they put different images of different people into the same pile. We also included 2 matching tasks. So these are tasks where we showed people 2 pictures and they just had to say same or different. We used images from the Glasgow task, which shows tightly controlled images. that are grayscale. And then Kristen developed the ambient image face matching task, where we used colored images that were natural. And then in the bottom right, you can see a lineup task. And here participants were given one image at the top and an array of 10 images. That first image is not in this array. The question was, is that person in the array? And if so, they had to click on that image. And if not, they could say target absent. So what we measured for the sorting task was number of piles, number of confusion or intrusion errors. For the two matching tasks, we used D prime and criteria. And then for lineup tasks, we looked at the proportion correct responses. And then as a way of getting at response bias, we measured the number of times that people said absent. All right, so what we can do then is do a principal component analysis to see how performance on these tasks hangs together. So I'll just tell you that, I didn't explain that they did this whole battery of tasks twice. So a week apart. And in the two batteries, we had all different images. So there was no image shown twice so that we couldn't get any kind of learning. And correlation across days was really good. So the performance definitely is stable, both in terms of D prime and criterion. So then what we did was we took our day one data and did a principal components analysis. So this is the outcome of that. And I'll just draw your attention to the loading column there. So you can see that our PCA came out with two components. And what loads onto that first component is D prime on our two matching tasks, the Glasgow face matching task and the ambient image face matching task. As well, on that first component, we see accuracy on the lineup task. And what's really interesting, and I'll come back to, is it's the number of misidentifications in the sorting task. So this component seems to have to do then with sensitivity to identity. The second component has to do with response bias. So here we have criteria, how liberal or conservative people are, their tendency to say same versus different. So we have criteria on our two matching tasks, lineup bias, which is the number of times that people say absent, and then the number of piles in the sorting task. So this was interesting because it changes a little bit how we think about that sorting task. We'd always thought of it as a measure of sensitivity, but it seems like that's true for misidentifications, but that the number of piles really has to do with your criteria. How much variability are you willing to accept as belonging to one identity? And then in experiment 2, we did exactly the same thing, except now we didn't test on 2 different days. All of the tests was on one day, but we created 2 versions of each task. So we dropped the sorting task, and now we had a simultaneous version, which is what I showed you. So the 2 stimuli are shown at the same time in our matching tasks. But then we created a second version of each task where we introduced a delay. So now in the matching task, first face comes up, disappears for 800 milliseconds, and then the second face comes up. And in our lineup task, they get to look at that target for 1500 milliseconds, but then it goes away before they do the matching task. And our question here was whether our principal components analysis would reveal a different set of components, perhaps whether memory was required or not. But that wasn't the case. So here's the results, and as you can see, the first component has all of our measures related to sensitivity, so D prime on the 2 matching tasks, and accuracy on the lineup task, and our simultaneous tasks at the top there, and our sequential tasks all come together. So people who are good on the simultaneous match are also good on sequential. And that second component is all about criteria, response bias, and all of our tasks load on that. So what we concluded from this paper was that, first of all, we should rethink the sorting task, and that the number of piles, which is what's so interesting, might reflect criteria, not sensitivity. So children, older adults, young adults tested with other race faces might be setting a different criteria. We can also conclude that individual differences in sensitivity and bias are stable. So nobody had shown before that this bias is stable. It's stable over time, and it's stable across tasks that have very different demands. So then what we asked is whether these individual differences might predict learning. We didn't look at whether they predict familiar face recognition because people are going to be at feeling, but might they predict differences in learning? This was important for us to ask because it might help us understand developmental data, but also it's allowed us to think more carefully about how we measure learning. And so now we're going back and redoing some of our developmental work, and I'll show you what that means. So this is a paper that just came out last year looking at unfamiliar face matching, predicting the slope of face learning. So not just performance at the end of learning, but performance as learning unfolds. So for this, what Kristen did, and you can get familiar with Kristen here, she's our training stimulus in all of these photos. So here, participants came in and they did our matching task. So again, the Glasgow task and our ambient image face matching task. This was to get a measure of individual differences in unfamiliar face matching. And then we did something very similar to what we had done previously, but we measured learning as it unfolded. So at the top there's C1, they got to see one image of the target, and then they were tested with images of that target intermixed with somebody else. Then they got to see 3 images of the target. The same images repeated plus 2 more, and then we measured learning again. Then they got to see 6 images. We measured learning, and 9 images and measured learning. So previously, all we've been doing is comparing the 1 image to the 9 image condition, or the 1 image to a 10-minute video condition. Now we're looking at learning as it unfolds. The other change we made here, which turns out to be really important, is instead of just saying, is this the person or not, we measured confidence. So now people can say, I'm certain it's not her. I'm pretty sure it's not her. I think it's her. I'm positive it's her. And this lets us get at the decision-making that's going on and gives us a richer understanding of performance. So the first thing, and I'm just showing you a bit of the data here in the interest of time. So this is showing you mean D prime on our learning task. And what we've done is a tertile split here. So based on the matching task, we have poor matchers, and you can think of these as what children and older adults might look like, mid-level matchers and good matchers on that matching task. And I'm showing you D prime on the learning task. I hope that makes sense. If not, somebody can put their hand up and go back to that. So we have poor, mid, and good matchers performing on our learning task. And what we're interested in here is whether there's improvement in D prime and whether there's an interaction. And we looked at this in 3 different ways. I'm just showing you one. Regardless of how you do it, you get an interaction. So what you can see here is that all 3 groups improved from that 1 image to the 3 image condition. That's what that asterisk tells you. But if you look at the poor matchers, they showed no further improvement. Whereas if you look at the mid and good matchers, they don't show any benefit from 6 images over 3, but they do show a benefit of 9 images. So people who are pretty good and very, oh, yes.
Can I ask, when you had them learn the, let's say 1, 3, 6 and 9 images, how long were they able to scan these images? I'm sorry, I missed that probably. I mean, did they have?
Oh, I didn't say that.
Did they have an unlimited amount of time, or or did they have a fixed amount of time for each of these conditions, like 10 seconds for the 1 image and 10 seconds for all the 9 images together?
Yeah, I'm quite sure it was fixed. I'd have to check the exact time.
Okay, yeah, no worries.
I can't recall. So, but it's an interesting question, right? Like, would the poor matchers do better if we gave them more time? looking at those images. I'd have to double check that though. Yeah, sorry, I can't remember that.
It's okay. It's okay. Sure.
Okay. Yeah. Okay. So what this suggests, and again, we've measured this, so we got another measure of slope. Regardless of how you look at it, we see continued refinement in our middle and good matchers, and not in our poor matchers. Now, then what we did, I think this is next. Yes. So okay. Then what you can do. And this was Kristen's doing, not mine. But what she was able to do is use those confidence measures and use the dual process signal detection model in order to look at familiarity versus recollection. So the idea here is that if you think about eyewitness testimony, you might see somebody and say, I'm pretty sure that I saw them at that scene, but I'm not sure if that's where they were. It's a sense that I know this person, but I can't consciously recollect from where. Whereas recollection is conscious. You can say, so if you saw me at the European Conference of Visual Perception in August, which I'm really looking forward to, and you'd say, that's Mondloch, she gave a talk, that would be a true recollection. So what we wanted to know was whether familiarity and recollection were showing different patterns of change across these three groups. So this is showing you changes in this sense of familiarity. Again, it's a graded response. There's no conscious recollection. And what you can see here is that we are getting very similar patterns across our three groups, where there's a big increase in a sense of familiarity after viewing 3 images. That's not surprising as compared to one. But we're not seeing any differences in our group pattern. So this can't be driving differences in the efficiency with which people are learning. You can then look at recollection old. And recollection old is this conscious recollection where you can think of it as a confident hit. You're sure you've seen this person before. And here what we're seeing are 2 main effects. So conscious recollection is increasing as people see more images, and it's higher in our good matchers as compared to our poor matchers, but there's no interaction. So differences in the slope of learning across these groups can't be attributed to conscious recollection. But we did see an interaction with recollection new. And recollection new is, you can think of as high confident rejections. You are sure that's not that person. And what's really interesting here is that our low matchers, individuals who perform poorly on an unfamiliar face matching task, showed no change in RN, no change in high confident rejections as they got to see more images of the target. Our mid-level matchers did show improvement in confident rejections, but not till they saw 9 images. Whereas the high matchers showed immediate improvement in RN after just seeing 3 images. So this suggests then that something that might be driving these group differences, and it's something that Kristen's pursuing now in her postdoc, could be this ability to discriminate, right? That you get better at spreading apart different identities. And as you become a better matcher, you do this more efficiently. So from this paper then, what we concluded was that matching ability predicts the slope of face learning, and this seems to largely reflect a relationship between matching ability and conscious rejection, or this RN. And what this makes us think is that how we mentally represent unfamiliar faces predicts learning. Now, we don't know what's driving this. We have to get to that yet, but it might vary with the number of known faces, so how many people you know. And it could also vary with general cognitive skills. That we haven't looked at. But I'll try to put this together for you, the little diagram that I made up in just a minute. So why do I care about individual differences given my interest in development? Well, we think that maybe these individual differences can provide us some hints about our group differences. So what we want to do now is start looking at learning as it unfolds in these different groups. For example, in children, in older adults, or in young adults learning a new other raised face. And we also need to go back to our group level differences and look at, start to collect confidence ratings so that we can see the extent to which group differences are being driven by these different parameters. It's also the case, and I'm not going to go into this, but I just want to flag it in case any of you have applied interest, that now that we know that group differences in D prime and sensitivity and criteria, so D prime and criteria, are stable across tasks and over time, we can think about how this might play out in applied settings. And so we have a paper that should come out this week or next. We've sent the proofs all back, looking at this in an applied setting, where we're looking at how people shift their criteria or response bias based on the environment in which they're making decisions. So we're trying to approximate border crossings, et cetera, where mistakes have costs and where the percent of match trials are not is not 50%. And what we show in this paper is that people do shift their response bias, but the extremity of bias that people adopt is affected by their sensitivity. So this means that in applied settings, all of this is going to lead to very different patterns of decision making. So this is just about out. And I had it in the talk, but I decided I was making my talk too long. So I took it out. Okay, so this is me trying to tie it all together and give you a hint now of what we're doing currently. So our thinking is that face matching predicts face learning. I think I've provided evidence of that. And that what we need to understand better now then are these individual differences in face matching. We think that these individual differences can be influenced or reflect differences in generic face space. So that first level of the DCNNs, as well as expert face space. So the one on the left might explain children better. The one on the right, young adults tested with other raised faces. I have not put general cognitive skills in, but if I could, it would be a translucent cloud over the whole thing. And that what's driving, we think, this generic face space, expert face space, is the number of familiar faces. Because again, if we think about DCNNs, every face that goes into that model is labeled. And so, but what I've also shown you is that face learning, you can imagine that face learning is also going to feed up to the number of familiar faces. If I'm a less efficient learner, like a 4- and 5-year-old child, it means that I'm going to be getting fewer familiar faces into my face space, which is going to then affect both my face matching and face learning. And something happens around 6, we think it's going to school, that suddenly you have enough familiar faces that you can start to learn more efficiently. So right now we have a couple of studies that are just in the middle of either this one's running and another one's getting set up. But we've decided to take this seriously and go back and look at young versus older adults. It's easier to get older adults in the lab, and they can do more than children. So we have them, again, doing a matching task. We have them doing Kristen's learning task, where we can measure learning as it unfolds, and they're making confidence judgments. And they're also making similarity judgments for another set of faces. And what we're thinking about here is, well, if older adults have different criteria than young adults, is it that their similarity judgments are different? So they think that faces look more similar, or their similarity judgments for matched and mismatched pairs are less distinct than we see in young adults. So we're going to look at whether it's that sort of perception of similarity versus the decision that's being made that's affecting their performance. But our prediction is that we'll get group differences in learning as it unfolds. We'll get differences in the dual process signal detection measures, and that this may or may not reflect similarity judgment. So that study currently ongoing. And then the other thing that we can think about is if we look at that, I keep pointing and I know you can't see where I'm pointing. If we look at the face matching tasks, a really interesting paper just came out, the lead author is Tim Andrews, that used principal components analysis to look at variability across faces. And what they conclude from that is that what adults are able to do, to some extent for unfamiliar faces, and even better for familiar faces, is ignore those early components, those early first sources of variability, things like head orientation and lighting that have nothing to do with identity. And our thinking is that children might have a harder time than young adults in ignoring those components, as might young adults tested with other race faces. But we're starting with children. And so we're working to see what happens if we remove these early components and whether that facilitates children's face learning and recognition. So it's a way of getting into this a bit more deeply. So I'll leave it there, and I can stop sharing my screen. I thank you for listening, and I'm very interested to hear your feedback.
Thank you, Cathy, very much. It was a really exciting talk. I'd like to ask everybody to unmute yourselves to give a big applause to Cathy for a great talk. And I'm, of course, opening the floor for questions. I actually have two myself, but okay, I'll have a go. So first of all, I want to ask whether you think, I mean, children, not only that they have less experience in viewing faces, but a lot of their interactions is of, of faces with, of child faces of their own age, let's say, and adults have, let's say, acquired the ability to, first of all, see faces across different age groups, but also see how a face evolves over, time, because faces really change, especially in adolescence. And so I'm wondering if this may also be an issue of, what their experience is. And the fact that they mainly are used to children's faces, and if I'm maybe I'm not correct, and you've tested adult faces in your studies, so I wonder if you have examined these paradigms with children's faces, and would they, for example, put less piles in a box? Or, anyway, if they'd be more precise, if it would have been, from children or from their class, or from a different class. And I also, I mean,
Yeah, that's a really good question.
The other is just another viewpoint. It's not, it's always talked about that, face perception is so amazing, given face, with familiar faces, because we can generalize across all these crazy viewpoints and lightings and etc. Across many manifestations of the way the face looks. But we are also we have specificity, so we can differentiate a face. Two, let's say, two twins, maybe too tough, but two brothers or two sisters, people who are very similar physically, but we can distinguish between them, just like we do with dogs and wolves, let's say. So it seems that the issue of not piling or piling into too many, putting it into too many piles, isn't that lack of generalization? I'm just thinking of it in another way. It's like you don't have a problem with the specificity, like with distinguishing, but you do have a problem with the generalization. It's just another thought about this aspect, but yeah, it's really interesting.
Right. Yeah. So I'll answer the first question first and then come back to that. So interesting. Definitely. So way back, 2004, I think, which seems really strange now, we published a paper looking at children's recognition of children's faces. But this was back in the day when a lot of my work had to do with sensitivity to feature shape and spacing. So we could take a face and swap out the one face's eyes with give a new set of eyes, would people notice this? We'd move the eyes in, out, up, and down. And so we had shown that children 8 years of age performed above chance. So they were sensitive to these cues, but they were less sensitive than adults. And in that case, we actually also tested them with 8-year-old faces. So they were 8-year-old participants tested with 8-year-old faces, and we didn't see that helped them. So there was still a difference between children and adults. And then we did a study, which when I think back to it, I could rewrite the study now as a different study, where we tested 4-year-olds. And our thinking here was exactly what you're saying. We thought if they're going to be good, they're going to be good with 4-year-old faces. So we tested them with 4-year-olds we wrote a storybook about Johnny and Susie and their day at the farm. And they took this book home and they saw multiple images of them. So that also goes to this idea of how long. They read that book at least 10 times. We tested them with their own face in the test, and we tested them with their best friends' faces. And no matter how we did it, the 4-year-olds were very sensitive to feature swaps. But if we changed feature spacing, they were a chance. So at that time, what we concluded was that even when we're testing children with child faces, they're not performing very well. But the tests were tightly controlled images. And so one of the things that Sarah Lawrence and I want to do is test children with child faces, because we think exactly that their face space, the number of known faces, those familiar faces are going to be predominantly will be predominantly children's faces. So they might do better there. Does that answer that question?
Yeah, definitely. And yeah.
So I think the other interesting thing about it is that we always tested children with adult faces because the logic was that from infancy, the faces that children see most, and both Meg Moulton and Linda Smith have done a lot of this, children mostly see just 3 faces for the first few months of life. And then their face input is largely biased towards female young adult faces. So we always thought, test them with that, because that's the early input. That's where they have lots of experience. They're a lot of time around mom, and that other categories would come on board later. But that was before we started thinking about this building a big face space. So I think we do need to go back and test with children. And now your other question, I'm sorry, what was
about the generalization and specificity, that maybe they are lacking the ability to generalize across different, let's say, ways that the face looks, but they are good at, specificity, differentiating between faces, but not being able to generalize across different ways.
Absolutely. Yeah, so there's some really interesting work out there. Mike Burton's got a nice paper showing that within person variability is idiosyncratic, by which he means if you measure the way my face varies and your face varies and somebody else's face varies, our faces actually vary in different ways. So that's part of why learning one face doesn't really, it gives you a boost. If you know lots of faces, you've got a boost. But learning one face doesn't directly transfer to another face, he argues, is because the variability is idiosyncratic. But I also think the problem is there's so much variability within identities, and then you've got variability between identities. I actually rather suspect that there's like a threshold to how good we're going to get, because you've got to weigh these two things. And unless there is something systematic that we're all missing, I suspect that until somebody becomes familiar, we're always going to have some errors. So you're exactly right that we can't generalize familiar to unfamiliar. Yeah. It's a problem.
Thank you. In the chat, so Galia Vidan writes, thank you for a very interesting talk. And Sharon Gilad Gutnik, she's still here, but I don't know. I just Zoom installed itself with a new version and I can't see the previous messages. This is crazy. So I can only see Sharon's message from like a few minutes ago, but not the one she wrote like 10 or 15 minutes ago. So I'm showing you can unmute yourself and ask
No,
if you did it.
yeah, no, in the middle, I was asking a question about a slide, but then you addressed it, so I deleted it.
Oh, you deleted it. Okay, okay.
Yeah,
Because I
yeah.
thought it's my new Zoom version that doesn't allow me to see older
No, I
messages.
don't think so.
Oh, okay, okay. So do you want me to read you what you wrote? You may want to check out. There's, I guess that's something in your lab. Xbox.
Yeah, Xavier Boyks, he was in our lab. He's now in the industry, but just some of the later publications from the last couple of years, we're kind of getting at a lot of these out of distribution learning, face learning questions, specifically in DNNs. So I saw that you kind of touched upon it. You might want to just check out some of that work.
Yeah, so
definitely. Yeah. Thank you.
Okay, and Ruti Kimchi also says thank you very
So
much.
if you're, can I put a little plug here to there's DCNN people in the room because I keep begging and nobody's going to do this, but I keep asking somebody to, because I think, and I understand it's a lot of work, but Linda Smith's work, I mean, it's just so beautiful. If you just want to read beautiful, beautiful work, or you can hop on and watch one of her YouTube talks, but she points out that what the DCNN models have never done is captured learning as it happens developmentally, right? And she's really interested in object learning, that it applies to faces. So the DCNN models, right from the get-go, are given these millions of faces and thousands of identities. But in development, what actually would happen is you get, you know, maybe thousands of images of one identity and several hundred of another, and maybe another of a third, and then the odd other face that's not labeled, and gradually adding faces. And I'd love for somebody to do that, because I wonder if it would start to replicate some of our findings. Yeah, so I think.
Who did you say? I just didn't catch a name.
Oh, Linda Smith. She's at Indiana University.
Yeah.
She's a
Yeah.
developmentalist.
Amazing stuff.
Yeah.
And she's actually showing that it's like a child giving kids who give themselves lots and lots of variability in an object in their hand, as compared to children who provide themselves less variability. That predicts differences in early language learning.
Right.
But I'd really love to see a DCNN that's got the human developmental experience and whether it would replicate. But I can't seem to get anybody who wants to put that.
Yeah, so I think he's touched upon that a little bit, Xavier. He's touched upon that a little bit, but still, you know, it always is based on these networks that at least have general training, and then you can like slowly add more specific within category training. But I think I assume, you know, I've worked like you with people with DNNs. I don't really run them myself, but I assume that there's a problem there with actually getting any kind of result if you don't have any training at all, right? Or if the training is very minimal and not variable, you would just get a whole lot of false alarms. But I know it's complicated. We've talked about it in our lab, but I don't think anyone's really done the same kind of slow introduction.
No, and I think the problem is going back. I might be familiar with some of the work that you're talking about. So there's a poster at BSS, which was really interesting, looking at whether it's the number of identities that matter or the number of images per identity. There was some kind of interaction there where the more identities you knew, if I'm remembering correctly, the fewer images you needed in order to produce learning. But yeah, I think it's a matter of you'd have to restart a whole DCNN, whereas people, if I understand it correctly, you get one that's been trained, you decapitate it so it doesn't know any identities, but it's got that basic training. And I want to go back to before that basic training. And Linda Smith would argue that you actually might ultimately have a better DCNN, because humans, I mean, we're so good with familiar faces, that the DCNNs actually might be better if we took that approach. But yeah, so I just keep throwing it out there in case somebody wants to run with that idea.
Okay, Cathy, thank you very, very much for a really great talk.
Yeah, my pleasure.
Very exciting, and thanks for being here with. Next week we are again on campus, so there won't be a Zoom talk, but I hope that in 2 weeks and later on we'll get back to our Zoom talks. We'll resume the Zoom talks so we can be in touch. And thanks so much again.
Great. Thank you for having me.
Thank you very much. So, bye.